Hello viewers and welcome to another episode of Space Science with Python. Today we are starting with the coding part of our Near-Earth Object project, but before we start I would like to talk with you a little bit about the next videos in the next couple of weeks. So as you may know or see, the summer is coming up a little bit, so it's getting warmer and nicer and you can do a lot of outdoor things, and this also applies for me. So my suggestion would be that the coding parts will be every second week. So yeah, I don't want to code all the time. I would really like to enjoy the weather outside. But in between though, I would like to provide some kind of space science videos. So I'm not the animation guy. I cannot really create nice animations or so. It's more like about picking up a certain paper and going through the paper with you and really try to understand what's in there. Like for example, active asteroids or other topics. Some topics that are um yeah, that are understandable, let's say, on that I can translate a little bit into a smaller video, and also maybe take my iPad and draw something to really make the science behind it more understandable. So I just wrote with some of you in the YouTube comments, and yeah, you second the idea also to reduce the cadence of the coding part, and then in autumn we will continue with a weekly cadence. But yeah, just let me know if this is fine, or what kind of cadence you would like to have. And in the meantime, I will throw in some space science videos. But anyway, today we are starting with the Near Earth Object project. And what we do first is we need data, and we need two kind of data. The second one will be introduced a little bit later in some other videos, but first, the first data set is actual near-Earth object data. And you may recall from the Comet video that we use the data from the Minor Planet Center to download it, to parse it, and to put it into an SQLite database. And we do something similar today, but we will not use the Minor Planet Center, but another service from the European Space Agency, ESA, called NEODyS. So this is NEODyS. It's a very simple web page that contains, or that condenses all near-Earth object information quite well. So we have here the home site, we have here the objects. If it loads, okay, that's a little bit slow. Where you see all the objects here, for example, also an ASCII file with all the names. We have also for each object all information. Everything is, it's a link, so you can really click on something like, for example, this object here, and then you get all the Keplerian elements, some other useful information, ephemeris information, and so on. So if you click here on more information, then yeah, we get here some more stuff. Also the intersection between Earth and this Earth, or the closest distance between this object and Earth's orbit. There's also some kind of animation, I think. I don't know if it runs on Safari. Well, maybe I have to run it on Firefox. Oh, I'm actually on Firefox, so I don't know. Maybe this is a new feature or so. I'm visiting this web page quite frequently, and it changes all the time. So they add more and more features. So I think this will grow over time quite nicely. They also put up all the codes and observation names. So for example, Greenwich, here you see Leiden, Utrecht, and so on. So there are all the observatories here, where you can also see so all the information. Well, Greenwich, the longitude is at 0.0. That shouldn't be a surprise. We have priority lists, the near-Earth asteroids elements also, so there are some elements here as well, and so on. And of course, more information. Yeah, so it's quite condensed and nice. I like this page, and we will use this information, this page, to extract our data today and to create our SQLite database. So how are we going to do this? Well, first of all, we need the raw data. We need to download it. And so let's first create our directory. We have here now our project folder, and you see the raw data has already been created. You can just delete it so that you see that it works. And it's interesting here that the syntax of pathlib. I don't know if I have shown you pathlib. So pathlib creates path objects, so not really strings but objects, For example, with directories, file names, and so on. And I actually like also working with it, also the syntax. So for example, you define here the directory, like for example, raw data, and the file name, which is called NEODyS.cat. And if you want to merge them both together, you just write here this line with a slash in between. Yeah, it's not like this raw data dir is divided by file, but it's really more that it appends this to a directory string. So if we just execute this here, you see that it's now one string where the NEODyS data will be stored. It's quite simple, but yeah, I like it. So it's a very nice structure, especially if you have larger projects or if you have some create some library in Python or so. It can get a bit chaotic if you only use strings all the time. So I would really emphasize that this pathlib library, it's also one of the in the standard library repository, that it's really useful thing. Now, before we download the data, I would also like to see if we also downloaded everything. So we need to extract the current number of all NEOs. And for this, I'm just opening this this page here, objects on NEODyS. So this is this link here in cell number 2. And on the very top, we have the current number of objects, 29,049 objects. So I'm extracting this information with from this HTTP response, and I use a regular expression here to extract the information. So how can we extract this part here? Of course, we can also simply trust our ASCII file. If a few neos are missing, nobody cares. But maybe this is also a little bit like a small hint that maybe in the future we will also work a little bit on how to crawl data or information from websites, because sometimes they do not provide a nice API and they do not provide a nice CSV file to download. So yeah, let's extract this here by showing the source information of the site. Yeah, unfortunately, this is not here in German, so you have to make a right click here in Firefox, and yeah, the very bottom, it's like, I don't know, exploration or analyzing. And then you see here the HTML code. You click here on the small arrow, you hover over this one here, the number, and you see the corresponding HTML part where this number is being shown. So here 29049, and we need this number here between this B tag and this B tag and where the word objects is in. So this is what we do here in this line. So we want this number here in between objects, between this B tags. And this is what we do here. We extract this, and then afterwards we can simply print the number of currently known NEOs. Of course, if we now download the file and in the meantime this website is being updated, well, this is bad luck, but I assume this will not be done in the next 5 minutes. Cell number 4. In cell number 4, we are now making a request to the website where we download the NEODyS data. It's called NEODyS.cat. So this is also the file name on the very top I defined. And then we just create the path lib object and then simply download the file and write it into a text file. So let's execute cell number 4. Now this may take a moment, and we see here now in raw data this NEODyS.cat. Perfect. So so what do we want to do next? We would like to create an SQLite database. And of course, I already created the SQLite database. So yeah, I can delete the database. Maybe here the not comments, but the NEOs. Let me delete it. The resulting database has a size of around 4 megabytes, and it's not encouraged to upload larger files on the Git repository, but 4 megabytes is quite okay. And public repositories can have a size of, I think, around 500 megabytes on GitHub. So I'm just uploading this so you don't have to download it. But yeah, if you would like to recreate everything and understand, delete the database and just execute the scripts here so you get a little bit familiar with the scripts. Cell number 5 is now something also very simple. We are going through the file. We are iterating row by row. Of course, you could say, hey, why don't you use pandas, read CSV or sometimes? Well, I have to say, sometimes I really like also using the standard methods in Python, just to keep in mind how things work in Python, not using all the time all the amazing libraries, of course, but just to not forget the basic knowledge. Of course, this can also be done better. Yeah, I know. If you show your code to another coder, he or she finds thousands of errors, but not the other way around, right? So this is what we do here. We read the file and then we iterate line by line and extract the information that are of interest. So let me maybe just show you how this file look like. And here we are with the raw data, opening them in the Atom editor. Just some other scripts here. And this is how the file looks like. We have the name, we have the epoch and modified Julian date, we have the semi-major axis in AU, eccentricity, inclination, longitude of ascending node, the argument of pericenter, mean anomaly in degrees, we have the absolute magnitude, the slope parameter, and non-gravitational parameter. We covered the orbital elements in the past, so just head back to one of the videos where I'm talking about the orbital elements. But here the other ones, like the slope parameter, the absolute magnitude, we will use these values in the future. Not now, but keep this in mind that we will also need this data. So let's head back to the next cell. So let's first execute cell number 5. And we have a dictionary now. And now let's see if we have as many NEOs as the website provides. So does the file contain the same number of NEOs as the NEODyS website? Yes, if the length of the dictionary is the same as the number, otherwise no. Crossing fingers, and yes, we have the same size. Perfect. So let's take a look here how it's been read. It's now a list with dictionaries, and each dictionary is a NEO. In the next cell, in cell number 8, we can now create our NEODyS database. So the NEODyS database is also here. We create a pathlib object to our dictionary and the database itself. And then we use SQLite 3 to connect to the database. Connection means that if the file does not exist, it's being created. And that's how we do it here. So let's execute cell number 8 and move to cell number 9. Where we simply create a table, a single table called main, and we put the name, the epoch, semi-major axis, and so on, and the column as columns, and then we use the execute many command to fill in the data with the dictionary that we just created. So let's execute cell number 9, and in cell number 10, I would like to add 2 more columns, namely the Aphelion and the Perihelion of the objects, because they're not part of the file. So we have to create the column. So we alter the table and add a new column. The column is Aphel AU or Perihel AU. It's a float number, and then we try to execute it. Otherwise, it's being passed. Because if you execute it, although the columns already exist, an SQLite operational error will emerge. So yeah, we just catch up this exception if we execute it accidentally several times. So let's do it here, cell number 10. And then finally in cell number 11 and 12, we are then filling up the data, updating the database with the Aphelion and Perihelion values. So how do we do it? We are simply selecting the name, the semi-major axis, and eccentricity. So the semi-major axis and eccentricity are the only values we need. So we fetch all the data. And then afterwards, we iterate through every NEO. And for the Aphelion, we use the the eccentricity plus 1 times the semi-major axis. This gives us the Aphelion, so the sun farthest point. And to get the sun closest point, we say 1.0 minus the eccentricity times the semi-major axis. And, no, this is not a mistake. No, that's right. So we have here the eccentricity, and here the semi-major axis, and then recreate the perihelion values. Again, we apply the execute many command, so we say we update the main table and set the Aphelion values here where the name equals the name. So the name is the primary key, it is the name of the NEO. Like, for example, you just saw it, Ganymede was one name, or Eros, and so on. So this is what we do, and then we close the database. So just let me execute it here and here, and we are done. So let me show you where's now my directory. Let me show you now. There it is. Let me show you now the database. And the database, again, is also in the Git repository. So we have here databases. We go then to NEOs, and we have here the NEODyS.db. If you have the SQLite viewer, you can simply double click on it and open the database. So yeah, we do it now here. And oh, there's an update. Good for you. We have here the main table with all the columns, and we have here all the corresponding data. Of course, you may say, well, we could put this everything in a CSV file or Parquet file or whatsoever, but I don't want to recycle all the code for all the sessions. So let's work with the small database. It's only 4 megabyte. It's not really big. And SQLite is really lightweight. So this runs smoothly and quick. So yeah, here are the names. You see the designation numbers. We have here the epoch, semi-major axis, and so on. So this is now our database we will work with. So the summary and the outlook. So today we just fetched the data for our future analysis. And the next time we will take the data and take a look at the distribution of the orbital elements. Because, well, humans tend to classify everything, and also NEOs are classified in a way. So before we compute or try to understand how these objects move in the night sky, let's first do some basic statistics and also classify our objects and see what these classes all imply. Very well. I hope you enjoyed today's session. It's a little bit about data fetching and creating SQLite database, so maybe it's something new for you. And if you would like to start already with some statistics here, then go ahead. Everything you need is now in the database, so you can use either the SQLite browser or Python or any other programming language you would like, and start doing some statistics on this, maybe comparing it with the Minor Planet Center or the ESA website or what's or not. And next time we will do it here on this channel. I wish you a very nice weekend, or the rest of the weekend. I hope the sun is also shining for you guys. And yeah, see you next week. Talk to you later.